My name is Ramesh HG, Assistant Professor of Mathematics, Government Postgrad College, Chittoor. Today I am going to explain subgroup concept. So we know what are groups. So group is a non-empty set under the binary operation star which satisfies the properties like closure property, associative property, identity property, inverse property, and commutative property. Closure property means for all a comma b belongs to G, a star b belongs to G. Associative means for all a comma b comma c belongs to G, a star b star c is equal to a star b star c. Identity property for all a belongs to G, a star e is equal to e star a is equal to a. Here e acts as identity element. So every group consisting of unique identity element. And fourth property is inverse property. For all a belongs to G, a star a inverse is equal to a inverse star a is equal to identity element. And commutative property, a star b is equal to b star a for all a comma b belongs to G. If it satisfies all these properties, then G is called an abelian group. If it satisfies only closure law, associative law, identity and inverse property, then we call it as group. So examples for groups are set of all integers, set of all rational numbers, set of all real numbers. These are all groups, or these are all abelian groups under addition. And set of all non-zero rationals, set of all non-zero real numbers forms a group under multiplication. 0 acts as identity element under addition. 1 acts as identity element under multiplication. And modular groups, these are also groups. Z2 containing 0, 1 is a group under addition modulo 2. Z3 0, 1 to 3, 0, 1, 2 is a group under addition modulo 3. Z4 0, 1, 2, 3 is a group under addition modulo 4. So like this, these are all several examples for group. Set of all matrices, 2 cross 2 matrices forms a group under addition. So these are all some examples of groups. Next we are going to teach about subgroup properties, subgroups concept. Let G be a group with binary operation star. This group can have a subset S, which is a group by itself under the binary operation star. Such groups are called subgroups, subgroups of group G. If H is a subgroup, it must satisfy two conditions. One is H is a subset of G, another is H is a subgroup of G under the same binary operation star. If G is a group under addition, then H must also a group under addition. If H is a subset of G, then H must also a group under addition. If G is a group under multiplication, then the subset H must also a group under multiplication. Then we say H is a subgroup of G. So it satisfies two properties. One is H is a subset of G and another is H is a subgroup of G. Subgroup means H also satisfies all the properties, that is closure, associative, identity and inverse and commutative properties. Then we say H is a subgroup of G. Definition: a subset H of a group G is said to be a subgroup of G if H itself a group under the same binary operation defined in G. A subgroup, a subset H of a group G is said to be a subgroup of G if H itself is a group under the same binary operation defined in H or defined in G. So let G be a group. The subgroups of G are 0, G and 0. It contains set containing 0 are called improper subgroups of G. So that means every group has at least two subgroups. You take any group which contains at least two subgroups and they are called improper subgroups. For example, if you take set of all integers containing positive integers, negative integers and 0. So the subgroups of Z are Z itself and set containing 0 element. Set containing 0 element. These are the two subgroups of any group G. So these two are called as improper subgroups. These are called as improper subgroups. For example, set of all integers. So you take Z as set of all integers, then Z and set containing 0 are the two subgroups of group Z. And these are called improper subgroups of G. So any group contains at least two subgroups. One is group itself and another set containing the identity element. The subgroups other than G and set containing identity element are called proper subgroups. So the G and set containing identity element are improper subgroups and the subgroups other than these two are called proper subgroups. So here observe that the group I plus, that is set of all integers, is a subgroup of Q plus. As we know, I is a subset of Q. Then Q is also a group under addition. And subset I is also a group under addition. Therefore, we say set of all integers is a subgroup of Q plus. Similarly, set of all rational numbers is a subgroup of R plus. So these are all under addition. The group R plus is a subgroup of C plus. So here I is a subset of Q, Q is a subset of R is a subset of C, whereas Q, R and C are groups and these are called subgroups. I is a subgroup of Q, Q is a subgroup of R is a subgroup of C. So let you consider this is fourth roots of unity. G 1 minus 1 I minus I is a group under multiplication. So fourth roots of unity, so these are the roots of the equation x to the power of minus 1 equal to 0. So on simplification we got x square plus 1 into x square minus 1. X square minus 1 is equal to 0 implies x equal to plus or minus 1 and x square plus 1 is equal to 0 implies x equal to plus or minus square root of minus 1, that is I. So in total the roots are 1, minus 1, I and minus I, and these four roots are called fourth roots of unity. And you write all the subsets of G first. We have to write all the subsets of G. First subset is 1 containing 1 and minus 1 I minus I and 1 minus 1 1 I 1 minus I minus 1 I minus 1 minus I and I minus I. So set containing 3 elements, these are all 3 elements, set containing 2 elements, set containing 1 element and the set itself or group itself. So you observe that among all these subsets, only first set, that is containing 1 and second one is 1 minus 1 and 1 minus 1 I minus I. These are the only three subgroups of G. Because if you take -1, -1 into -1 is +1, so 1 is not there in this set, so it is not subgroup. You set containing I into I is I square -1, so this is not a subgroup. -I into -I is minus I square -1, so -1 is not there in this set, so this is not a subgroup. 1 minus 1, this is a subgroup because 1 into 1 is 1, -1 into -1 is 1, 1 into -1 is -1, so this forms a subgroup of G. And 1 minus 1 I minus I, this is already this is a subgroup of G. So totally 1, 2, 3, 3 are the subgroups of G, and here first one 1 and last one are called improper subgroups, and this is only the proper subgroup of G. So this is the table for this one. 1, 1 minus 1. So in total 1, 1 minus 1, 1 minus 1, I minus I. These are the only three subgroups of G, and first one and last one are called improper subgroups, and second one is called proper subgroup. So you observe that the structure, the multiplication table, 1 into 1 is 1, 1 into -1 is -1, -1 into 1 is -1, -1 into -1 is 1. So all the elements are the elements of H, and 1 acts as identity element, and inverse of 1 is 1, and inverse of -1 is 1, inverse of -1 is -1. Therefore, since it satisfies all the properties closure, associative, identity and inverse, and hence it is a group, and hence it is a subgroup of G is equal to 1 minus 1, I minus 1. So this is the group structure. This is the group structure 1 minus 1, I minus I, and 1 acts as identity element -1, inverse of 1 is 1, inverse of -1 is -1, inverse of I is minus I, inverse of minus I is I, and hence this is a group structure. Algebraic structures next, let Z is equal to -3, -2, -1, 0, 1, 2, 3. So this is a set of all integers. That is set of all integers, and it satisfies all the properties of groups: closure property, associative, identity and inverse property. Associative and inverse property, and 0 acts as identity element. Inverse of 1 is -1, -2 is inverse of 2, -3 is inverse of 3, -4 is inverse of 4, like that. So every element has its own inverse, and 0 is a unique identity element. So therefore it satisfies closure property, associative, identity and inverse property and commutative property. Therefore it is a group under addition. Next you take this subgroup or subset first. Subset. So 2Z. You take multiples of 2. Multiples of 2, you take multiples of 2. So multiples of 2 means 2Z. It consisting of multiples of 2, that is -6, -4, -2, 0, 2, 4, 6 and so on. You observe that 0 acts as identity element under addition, and -2 is the inverse of 2, -4 is the inverse of 4, and clearly 2 plus 4 is 6, -2 plus 2 is 0, -4 plus 4 is 0, or -2 plus 4 is 2, so it satisfies closure property. Similarly, it satisfies associative property. Similarly, it satisfies identity property. Similarly, it satisfies inverse property. So every element has its own inverse, and hence it satisfies commutative property also, Therefore, this is a group structure and this is subset of Z. Therefore, we call it as it is a subgroup under addition. It is a subgroup of Z under addition. Similarly, you take 3Z. This is multiples of 3. So 0, 3, 6, minus 3, minus 6 and so on is a subgroup under addition. So as you know that 3 plus 6 is 9, minus 3 minus 6 is minus 9, 3 plus minus 3 is 0, so it satisfies closure property. 0 is the identity element, inverse of 3 is minus 3, inverse of 6 is minus 6, inverse of 9 is minus 9, like that. Every element has its own inverse, and hence it satisfies commutative property, and hence it is a group under addition, but it is a subgroup of Z. Therefore, we call it as 3Z is a subgroup of Z under addition. Z is equal to set of all integers is a group under addition, and Q P by Q. So numbers in the form of P by Q, where P and Q are integers, is a group under you take Q minus 0 here, Q minus 0, set of all non-zero rationals, is a group under multiplication. Then you take H as a subset, which is equal to 2 to the power of n. So 2 to the power of 1, 2 square, 2 cube, 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3, etc. So H is equal to 1 by 8, 1 by 4, 1 by 2, 1, 2, 4 and so on. So if you multiply 2 into 4 is 8, 8 into 2 is 16. So 1 by 2 into 1 by 4 is 1 by 8, like that. Or 1 by 2 into 2 is 1, 1 by 4 into 4 is 1. So 1 acts as identity element. 1 acts as identity element. Inverse of 2 is 1 by 2, inverse of 4 is 1 by 4, inverse of 8 is 1 by 8. So every element has its own inverse. Therefore, it satisfies closure, associative, identity and inverse element, and hence it is a group structure, but this H taken from Q, set of all non-zero rationals, and hence this is called as a subgroup of non-zero rationals. It is a subgroup of non-zero rationals. So these are some examples of subgroups. These are some examples of subgroups. So thank you. So today we have studied subgroups and some examples. Thank you.